Good day everyone, welcome to my video. My name is Paul Lee. I'm a master's student in mining engineering working under Dr. Ilya Moskovic. Today I'll be presenting my research on numerical model for predicting rockfall corrosion. A major challenge in underground mining is the monitoring of rockfall corrosion, especially on the boat exterior. A solution is to numerically simulate the corrosion of rockfall using the electrochemical property of minerals. My approach can be broken down into 3 steps: input characterization, simulation, and validation. I made 2 types of sample electrodes: a larger rock core electrode collected with 3/4-inch diamond hole saw, and a smaller single mineral electrode using 1/4-inch hole saw. Here is the polarization curve of argillite and steel. Using linear sweep photometry in a 3-electrode system, I plot the current density in log scale against the applied potential. We're interested in the intersection of cathodic and anodic curve, which marks the corrosion potential approximated by steel open circuit potential and the corrosion current density. We do the same for other samples. Some are anodic to steel. Others are cathodic to steel. I also measure the conductivity of mine water as a parameter in the simulation. To simulate rockfall corrosion, I'm using ANSYS Fluent, a commercial CFD with native electric potential solver. Using a custom user-defined function, I track the corrosion damage with moving boundary. Assuming the gap between bulk and rock is filled with water, we simulate the fluid domain bounded by steel rockfall and host rock with heterogeneous mineralization. Here you see a simplified boundary condition with individual current density for segmented minerals and constant potential at the steel surface. The UDF I use to track the corrosion damage calculate the corrosion rate of steel as a function of equivalent weight of steel and current density over valence number, Faraday's constant, and density, where current density is electrolyte conductivity times the negative potential gradient that is solved by Fluent. This is a chronological example of my simulation. Here you see sample 19, a slice of oval core sample you saw in the beginning. It has been polished to 3000 grit to show mineral color without wetting. Here is sample 19 photographed under microscope. Here, microscopy image is segmented by color of minerals. Depending on the minerals, other technique may be necessary for segmentation. The resolution is drastically reduced for shorter computational time while keeping the spirit of mineral distribution. Here, the segmented image is turned into high-definition cut cell mesh. Tetrahedral and hexahedral mesh are also used in other samples when appropriate. Here is a contour plot of electrical current magnitude on the steel surface for sample 19. Here is a contour plot of Z-mesh coordinate on the steel surface representing the corrosion depth at 100 days in the simulation. Here is the steel plate zip tied to sample 19 after 100 days of submersion experiment in mine water. Here you see the validation experiment, where bulk samples are zip-tied against steel plate and submerged in mine water for 100 days. The steel plate is then examined under confocal microscope. The submersion sample showed matching corrosion profile with the simulation, except for an anomaly in the center where samples are held so tightly against the steel plate, mine water could not penetrate. As a final step, the bulk samples are pulverized for X-ray powder diffraction to positively identify mineral content. In summary, linear skin photometry can determine if a mineral is galvanically corrosive to steel. That by itself is a useful tool in monitoring corrosion. Simulation takes additional steps by accounting for conductivity for groundwater and geometry of the domain. This can be very helpful to a geotech engineer.